actor workflows. So if you've joined us today for a talk about your favorite Netflix actors, I'm sorry to disappoint you. This talk is not about that kind of actor. Today, we'll talk about how we leverage temporal workflows and the actor model in order to build a reliable and scalable control plane to manage 12,000 Flink clusters that process 60 petabytes of data in real time a day. My name is Jorge, and this is my colleague Mark, and we work on the data platform team at Netflix. So for this presentation, we'll breeze through a brief introduction of Apache Flink and how we use it at Netflix. We'll then also highlight some of our challenges. We'll then take a deep dive into our actor workflows architecture, and we'll review some learnings from our experience building and operating the system over the past 2 years. So what is Apache Flink? Apache Flink is a framework for processing streaming data at large scale. Developers can write applications that can read from various sources, process and transform that data in real time, and then output to various sinks. For those who may be familiar with Apache Spark, Apache Flink is similar, except that Flink's real strength is real-time processing, whereas Spark, main strength is batch processing, though both frameworks can handle both types of workloads. At Netflix, we leverage Apache Flink for various use cases. One is data pipelines that join and enrich streams of events and build user sessions to gather user insights. It is also used for event-driven applications that power membership, billing, and subscription events, and real-time machine learning feature generation to power our user recommendations. The data platform team at Netflix has also built fully managed data movement abstractions which leverage Flink to easily enable movement and transformations on data with a few mouse clicks. A Flink application runs on a cluster. To keep it simple, the main things to know about a Flink cluster is that there are two key components to provision. There is a job manager server group and a task manager server group. Additionally, Flink applications are stateful, and only one version of the application can be running at any given time. This makes Flink deployments susceptible to concurrent changes, which may interrupt or conflict with each other. So careful sequencing of changes is required. This is where our platform's control plane steps in. It is a service responsible for managing the full life cycle of all of our Flink clusters. Users or other system components invoke the control plane APIs and to make changes to their running Flink applications. The control plane then processes these requests and schedules changes to be executed in a safe manner across the fleet. Our control plane is the component where we leverage temporal workflows and the actor model for our complex orchestration needs.
So how did we design this control plane? We chose to use the actor model implemented with Temporal. Managing Flink cluster has a lot of parts to it, and using actors helped us to simplify the complex logic. Before we dive into the details, let's briefly cover the basics. So the actor model is actually an old idea which originated in the 70s to model concurrent computation. So what is an actor? An actor receives messages, it processes these messages, and stores some state internally. And as part of processing those messages, it might send new messages to other actors or spawn new actors in the system. The internal state of an actor cannot be directly accessed by other components. So when we think about the actor model, you can think of it as representing your system with many different types of actors. The key idea is while actors can modify their own state, in order to modify the overall state of the system, it can only do so by sending messages to other actors. So in object-oriented programming languages like Java, you model everything as an object. And similarly, when you're using the actor model, you model everything in your system as actors. So why is this abstraction useful when building concurrent and distributed systems? Usually when you're working with concurrency, you may need low-level concurrency control mechanisms like locks and synchronization. However, it's easy to make mistakes with these concurrency mechanisms, and it can lead to problems like race conditions and deadlocks. And I don't know about you, but I personally don't like to debug deadlocks and race condition, especially after midnight. So Actor Model can help you design your system to avoid these problems in the first place. So what does this look like in practice? So let's take a look at how we modeled the Flink cluster orchestration. When a user wants to create a new Flink cluster, they interact with our control plane API, and two things happen. First, it creates a cluster actor. And this actor is a logical representation of our new Flink cluster. And two, a message is then sent to this new cluster actor saying a new deployment is needed for the new cluster. The cluster actor is then responsible for processing this deployment action message. It handles this by spinning up child actors called deployment actor to do the heavy lifting. Cluster actors can accept messages of different types, which can spin up different child actors to do different tasks, like we have with the SafePoint actor here. What about a more complicated example? So in the case of cluster actors, each actor works independently from each other. But what if you need to have some sort of coordination mechanism between them? So in our system, if all 12,000 cluster actors tries to redeploy at the same time, we're going to run out of resources and maybe get an unpleasant Slack message from our container management team. So how can we, at a system level, coordinate across multiple cluster actors? We have a limit on how many deployments can occur at once, which we model as the deployment resource actor. So how does this work? So each cluster actor will send a message to the deployment resource actor when it wants to do a new deployment. And it will block until it receives a response back. The deployment resource actor keeps track of all the pending deployments as well as new deployment requests. And depending on how much resources we have, we may rate limit some of the deployments. The deployment resource actor also encapsulates our business logic on prioritizing between multiple deployment requests. And when we have enough resources to continue, it will send a message back to a specific cluster actor, unblocking that workflow from continuing with their deployment actor.
So let's put that all together. The control plane APIs can be invoked by various external components, such as users using the UI, external services leveraging Flink as a building block, as well as cron jobs and automations making modifications to the underlying Flink clusters. When you create a Flink cluster through our control plane API, this creates a new cluster actor, which logically represents the underlying Flink cluster. This cluster actor will be alive for as long as the Flink cluster is deployed. Cluster actor then leverages child actors to do the heavy lifting logic. For example, we have 3 child actors that can spawn from the cluster actors in the diagram. But in reality, there are many more types of child actors in our system, where each child actor encapsulates some operation that we want to perform on our Flink cluster. In the examples here, we have a deployment actor that redeploys the cluster, a rescale actor that changes the number of instances in the cluster, or a SafePoint actor that takes a snapshot of the running application. There are other types of actors in our system. An example is the container migration actor, which is responsible for monitoring our container management system to detect if any of the containers in the cluster are running on degraded or bad instances, in which case a redeployment is required. In these circumstances, cluster migration actor will send a message to the cluster actor, which will spawn a new child deployment actor in order to actually handle the deployment task. So let's take a look at how this ties into Temporal. The actor model is widely used across various frameworks. For example, you may have heard about a popular library called Akka, which is an implementation of the actor model for the JVM. While this abstraction doesn't come out of the box with Temporal, it turns out it provides us with the basic building blocks required in order to implement the core ideas behind the actor model. We chose Temporal to implement the actor model due to the built-in scalability and reliability that you get from using Temporal, along with higher level building blocks. Temporal is an event source system where each event is persisted in durable storage. We don't have to worry about lost messages with Temporal because all messages are stored in the event history. Even in the presence of failures, Temporal makes it easy for us to recover our failed actors. We can also leverage queries in Temporal to be able to inspect the internal state of our actors, which is greatly helpful in debugging and operations. So let's take a look at how we can leverage the basic building blocks in Temporal to build actors. To start, we can implement actors using a long-running workflow in Temporal. These actors can communicate with each other using signals and queries. Each actor can be given a unique address using the workflow ID, and Temporal's workflow ID reuse policy helps us enforce the ID uniqueness constraint. And to spawn new actors into the system, we can spawn new workflows or child workflows from an existing actor if we want to create a parent-child relationship between the actor workflows. When creating child-actor workflows, we can specify the parent close policy in order to manage the life cycle of the child actor. For example, if we set the parent close policy to terminate on the child workflow, whenever the parent actor is terminated, the child workflow will be cleaned up as well. Now let's take a look at how this looks in code.
So let's start with a simple interface definition. To create an actor workflow in Temporal, we just need to define two methods in the workflow interface. The first one, a signal method to allow other entities in the system to message the actor, and a workflow method to start the actor. So in our example we have up here, we don't have any initial state to pass into the actor, but if you do, you can leverage the parameters of the start method. To implement the actor workflow, we'll start with the signal method. We call it message here. And in the signal method, we want to keep this simple. Because the signal method will be called multiple times and frequently, you want to keep it as simple as possible. So in our case, we're just taking the message and throwing it into a queue called mailbox. The actual processing of these messages will occur in the main processing loop of the actor workflow. Next, we'll implement the workflow method called start, and this will be our main processing loop for the actor. In this case, we have an infinite loop where we leverage the workflow.await function from Temporal SDK, and this specifies that we're going to block until we have a message to process. And once we have a message to process, we'll remove it from the mailbox and pass it to the process message method. And in this method, we want to ensure we wrap our logic in a try and catch to catch any unhandled, bubbled up exception from our processing logic. In our implementation, we typically log and output a metric when we encounter an unhandled exception, because we want to ensure that the actor does not get into a failed state. And if the actor ends up in a failed state, it means other components within the system can no longer interact with this actor. And finally, in the start method, we end our processing loop with check continue as new method. We'll talk a little bit more about this method in the later slides, but this is very important when using Temporal for long-running workflows. So we've been operating this actor system for a couple of years now, and we evolved it over time to implement new functionalities. And we learned a few things during the process. So here are some tips and tricks to think about when you're building your own actor workflows in Temporal. The first challenge is recognizing when actor workflows could be a good fit for your system. If you find yourself needing low-level concurrency control mechanisms, like locks, consider whether the actor model could be a better fit. Message passing will provide a basic form of concurrency control for your shared resource. If you need to manage and orchestrate many independent resources, the actor model can help. Each actor that logically represents your resource can independently manage its own state. And when modeling complex logic, consider breaking it up using different actor types, like we did with the cluster actors and all its child actors. When it comes to building out your actor system, it's important to keep the long-running actors as simple as possible. Think of these long-running actors as a state machine, and you want the state machine to track different state transitions, but you don't want the state management code throwing unexpected exceptions. So if you want to keep these long-running actor workflows as simple as possible, how can you implement complex orchestration logic? In this case, consider leveraging child workflows as child actors that spawn from your long-running actors. Your long-running actor workflow should delegate the complex logic into these child workflows, and for these child workflows, they should be relatively short-lived compared to your other long-running actors. This way, if there was an unexpected failure, you can easily retry the failed child workflows. When you're building your long-running actor workflows, think about how you want to deal with unexpected exceptions. If you delegated most of your complex logic into short-lived child actors, it's more likely that the child workflows will evolve and change faster than your parent actor workflows. This means that you're more likely to face an unhandled exception in the child actors, and parent actors should anticipate and handle these exceptions that bubble up. When it comes to evolving your existing actor system, there are a couple different approaches you can take to ensure backward compatibility with the running workflows in your system. This is especially important for long-running actor workflows, since you want these actor workflows to be ready to process new messages rather than failing due to a backward incompatible change. So for long-running actor workflows, we can leverage the workflow versioning mechanism from Temporal SDK. So in the code example here, the workflow logic used to call previous function, but we want to evolve the workflow logic to call a new function instead. We can leverage the versioning mechanism from the SDK by calling workflow.getVersion. This takes a change ID and string, which describes your change, a min and a max version specified as integers. When this code is executed for the first time, max version, which is 1 in our case here, is returned and a new function method is called. This creates a new version marker into your workflow event history, so during a replay, you will get a deterministic version back. But during a replay, if it didn't encounter any version markers, it's going to return the min supported version. So for any workflows that were running before our workflow evolution here, we'll continue to run previous function. An alternative approach to evolving actor workflows is to clone your existing workflow implementation as a new workflow. So it turns out this works relatively well for short-lived child actors, but it's much trickier to implement it for long-running actors in your system. But regardless of which approach you take, we recommend being disciplined about cleaning up your versioning forks and your old workflow implementation. Over time, if you have too many forks in your workflow logic, it's much harder to reason about the logic and state. But before cleaning up your workflow versioning forks, you have to be careful that you have fully drained any workflows that are using the previous version. Otherwise, you may encounter an unexpected exception when a replay occurs. And when it comes to cleaning up old workflow implementations, this is a little bit easier because you just have to ensure that your old workflows are no longer running in your system And after that, you're able to easily delete those from your implementation. And when it comes to operating the actor system, we want to be hands-off as much as possible. However, things don't go as planned, so we need to make sure we build the right operational control mechanisms in the system. To start, you should build various query methods in your system. This is especially useful for inspecting the state of long-running actors, but even for short-lived actors, being able to inspect the internal state is a powerful tool. And all you have to do is implement the query methods in your workflow, and Temporal provides all the tooling, including a UI, to visualize your actor state. You should also consider building various recovery mechanisms in your system. While we can try hard to ensure that long-running actors don't fail due to unexpected exceptions, things can slip through the cracks. When your actor workflow unexpectedly fails, as I mentioned previously, your failed actor can no longer take messages from other actors in the system. So ensure you have the levers that you can pull to get things back into an expected state and recover from a failure. As an example, we have built and used some manual endpoints that can recreate failed actors into a specific state. It's also helpful to have high-level mechanisms that can control multiple actors. So for long-running actor workflows that were created across different time, they may be running with many different versioning forks in their workflow event history. And this makes it very difficult to reason about the state of your entire system. It's hard to know which versioning forks are safe to delete and removed from code. And having a mechanism to safely truncate the event history across multiple actors can help with the issue. So for example, in our system, we have a mechanism which will safely recreate the existing actors with fresh event history, making it safe for us to clean up the old versioning forks. And when it comes to building resilient actor systems in Temporal, we need to anticipate failures that can occur in the system and build in mechanisms to mitigate them. For long-running actors, it's important to leverage continue as new mechanism provided by the SDK. So Temporal has a limit on the number of events in the event history of a workflow, as well as a byte size limit of the entire event history for a workflow. When running long-running actor workflows in Temporal, it's very possible that you may eventually hit these limits. Continue as new mechanism allows us to create a new workflow with fresh event history, allowing us to truncate the event history of an actor periodically. And this is more of a general Temporal advice, but it's especially important for long-running workflows to understand how event history maps to your workflow code. This will help you to reason about the changes that are backwards compatible and what changes will require versioning as you evolve your system. But if you're like Jorge and you don't make any mistakes while you're reasoning about your new changes, you probably won't need this advice. But for everyone else, we strongly recommend building unit tests to find non-deterministic exceptions at development time rather than in production on a Friday afternoon. So you can do this by downloading a couple event history of workflows from Temporal UI and playing these event histories against your workflow implementation in unit tests. And if you unintentionally made backward incompatible changes to your workflow, then these unit tests will fail and you'll be able to catch the non-deterministic exception during the development time rather than in production.
So let us close with a recap of our learnings. Consider designing your system using actor workflows in Temporal when building concurrent and distributed system. Temporal offers the necessary building blocks to leverage the actor model through signals, queries, and child workflows. It also helps you easily manage the lifecycle policies of actors through parent close policy and workflow ID reuse policy. When building your actors, keep the long-running actor workflow logic as simple as possible. You can accomplish this by creating shorter-lived child actors from these long-running actors. Delegate the heavy lifting logic to these shorter-lived child actors instead to help you isolate errors and failures away from your long-running actors. For any long-running actors, make sure to call continuous new in order to manage the event history size and count. And when you call continuous new, be mindful about the existing actor state that you need to carry over into the new workflow instance. When evolving your actor system, think about how you're going to version your logic. The easiest approach is to clone your workflow implementation with a different workflow name. This approach works well with short-lived child workflows. However, cloning workflow implementation isn't always the best solution. For long-running actor workflows, you may want to leverage the workflow versioning mechanism provided by Temporal SDK. As you evolve your system over time, number of versioning forks will grow, making it harder to reason about your actor logic and state. So make sure to take some time to clean up the versioning forks when it is safe to do so. And protect your system and yourself from non-deterministic workflow exceptions through unit tests and reasoning about your new logic on existing long-running workflows. To ensure smooth operation of your system, build operational control mechanisms. Leverage using queries from Temporal SDK to be able to easily inspect and debug your long-running actors. You should also think about building control mechanisms for recovering long-running actors that have unexpectedly failed or been terminated. And it's also helpful to have controls to be able to drain existing workflows and replace them with new instances of their corresponding workflows. So this brings us to the end of the recap and the end of the presentation. We'd like to thank everybody for attending, and Mark here is now available to answer your questions.